Hi. So in reference to the pi bonds that we are looking at, or what I'm doing in my course, I just wanted to have a quick look at molecules in three dimensions. I'm going to start by just looking at a very simple molecule of butane, just to illustrate an important point. So I've got this little model in front of me which we can play with. The skeletal structure, this is just butane, zigzag like that. The important thing to note with this model is that butane and any molecule like this is just composed of sigma bonds. All right, there's sigma bonds between the carbons, between carbon and hydrogen. Every single one of these single bonds is a sigma bond. It's the three-dimensional aspect of this which makes things a little bit more complicated, because I mean the way we look at it, it can spin around. Okay, these sigma bonds allow it to move and adopt many different shapes and conformations. All right, and that's what it tends to do in solution. But what we do know is that generally speaking, the molecule tries to adopt a conformation, and now what we're going to do is we're going to look on the side here, adopt a conformation when looking straight down the bonds. All right, it doesn't want to do this. It wants to kind of get the bonds and the other carbon behind it to be eclipsed. And what happens is that with each and every subsequent carbon-carbon, we end up doing that. And then the last one we look at, and we do it like that. And when we look at the molecule in the end, this is what it looks like in three dimensions, and put down on a flat piece of paper. Now you see the connection between this three-dimensional structure and the zigzag line that we draw as part of our skeletal structures. All right, trying to keep this roughly, I mean, the bond angle here is 109.5 degrees that we learned for tetrahedral carbons. When we draw it out, we estimate it to be 120. It doesn't matter too much. But what's important is to notice that when we look at this, you see this hydrogen that you see in front of you is the one that's pointing up, but the one pointing behind, you can't see it. Because this is a tetrahedral carbon, you cannot see the one behind it over there. So if we were to draw the hydrogens here, we draw a hydrogen, it would be straight up like that. The one behind we wouldn't be able to see. And so what we do is we cheat a bit. We twist the whole thing a little bit like that so that we get to see the hydrogens. And then what we have is a situation where we can say there's a hydrogen going forward and there's one going towards the back. All right. And obviously the little one that I did in the beginning there is out. Okay, and that's why we draw our skeletal structures this way. Notice carefully, and I'll do it on this carbon over here. This carbon over here, it's not a situation where we have a hydrogen going up like this and another one going to the back over there. All right. I hope you can see that from this structure, that drawing something like that is actually not consistent with the three-dimensional structure that we have of this butane over here. All right, so that's just butane. This is without any double bonds. What happens when we include a double bond and we get something that, for instance, just very simply is butene? Well, this is what we get over here. We get a molecule of butene, just turn it around, which is like this. All right, so here we have there's a methyl group here, and we're going to the double bond and the single bond over here to the other methyl group over there. The double bond itself, and I've exaggerated on this model, is made up of two p orbitals, all right, which are these massive green things over here. So this is one p orbital here. That's just one p orbital. It's not two different ones top and bottom. This is one whole p orbital. This is another whole p orbital. Each one has one electron. The electron could be there and it could be there. It actually doesn't matter where it is. It's just part of the whole orbital. And what happens is the pi bond is an overlap of these two orbitals, all right? Note, it's just two orbitals, 1, 2. They're going to overlap in the center, and that forms this pi bond that we have over there. All right. It is one whole new bonding orbital. It's not a top and a bottom half, two orbitals. It's one whole orbital. It might seem a bit weird to kind of think about it that way, but that is the way it is. All right, this is what it looks like at a quantum level. Okay, so what are the consequences of this? Well, the consequence of this is, first of all, this carbon and this carbon over here end up being tetrahedral. They are flat. All right, so if we look at the molecule down the side, it is completely flat. That is very important. Another very important consequence of this pi bond is, unlike the tetrahedral carbons of the butane chain that we had, this bond, which has the pi bond on it, there's a sigma bond and the pi bond, cannot rotate. All right, so if we go here, we cannot do this, because the minute we twist it like that, all right, we have now broken this pi bond. The orbital is no longer overlapping with this one over here. All right, it's no longer overlapping. So by twisting that bond, we have broken the orbital. And that means that when we have a molecule like this, or like this over here, which is the butene, which we know is trans-butene, this is on the opposite side, in order to change it to this one, which is cis-butene, we have effectively broken a bond and then reformed it. And that is a chemical reaction that needs to occur. All right, some type of reaction needs to occur. So we can't just do that. And so because of these p orbitals over there, they lock the structure into a particular configuration, and it cannot change unless we break the bond, all right, that has formed over there. Okay, I hope that helps you see these molecules a little bit better in a three-dimensional sense.